Today we'll be looking at a project called Supercavitation swaps. It was created for a rootstock hackathon in November 2018 by Lightning Network Chiang Mai. For more information, including technical documentation and source code, please check the description of this video or visit our website at lncm.io. A supercavitation swap is a way of trustlessly swapping Lightning Network Bitcoin into Ethereum virtual machine assets, such as rootstock Wei, Ether, or tokens on those networks. Supercavitation swaps are similar to atomic swaps, but with some extra features to make the process faster and more frictionless. The main benefit is that a party can swap from Lightning Network into EVM without already having EVM gas, as other implementations require. The system allows users to onboard into an EVM chain such as rootstock with just a mobile phone. Please note that the current implementation is a technical demo only. It's all on testnet, it's not been audited, and it's not intended for production assets. Now, let's jump into the demo. This is the user interface that our protagonist Alice will be using to interact with the Supercavitation service. It's a simple web app currently published to IPFS, but could be hosted anywhere. For the sake of this testnet demo, Alice begins by inputting a mnemonic that derives a rootstock address. In a real-world deployment, a more secure key store or hardware wallet system could be used. After entry, Alice's browser talks to a public third-party gateway node that is used to read the EVM chain. In production, this could be a locally running node. You can see that Alice's mnemonic derived into an address that already has an RSK balance. The current page has a list of swap offerings that are pulled from an on-chain registry. These various swap offerings are controlled by different third parties, and anyone can deploy their own. In this demo, we'll go through two different swaps, first showing a standard example with Bob, followed by a swap with Charlie demonstrating how Alice can safely claim her funds even if Charlie goes offline mid-swap. For now, let's have a look at Bob's swap offering. Bob's on-chain swap offering contract contains a URL that Alice can use to communicate with Bob's web service that enables her to make swap requests. Alice's browser verifies that the messages she receives from the server are signed by the same address that owns the swap offering contract. Each swap offering has various different configuration options, including a time lock, the number of blocks that the swap must be settled within, a minimum order amount, an exchange rate, or how much profit Bob is making from converting Satoshis to Wei, Wei being the smallest unit on the EVM side, a deposit fee to prevent Bob from being spammed, which could be waived if Bob trusts Alice, a close reward to incentivize Bob or anyone else on the network to publish the settlement transaction and enhance Alice's user experience, a supercavitation amount to give Alice enough gas to close the swap herself should Bob go offline. Right now, Alice already has enough Wei, but this gives new accounts with no Wei the guarantee that they can always make the claim should Bob go offline. And finally, the amount of funds available in the swap contract. These configuration options are chosen by the owner of the swap offering and are verified by Alice's browser before she makes a settlement payment. If Alice likes the look of the swap offering, she can make a request to Bob to create a new swap instance. Alice can see exactly how much she will be required to pay before making the request. When she makes the request, Bob creates two Lightning Network invoices. One invoice for the deposit fee, which, upon payment, will trigger Bob to create the swap on the EVM chain to Alice's specifications. This deposit is required to prevent Alice from spamming Bob and locking up his funds. A second invoice for the settlement payment itself. Upon completion of the settlement invoice payment, a secret will be revealed to Alice that the contract will consume and settle the swap. Thus, Alice knows that if she pays the invoice, she will always receive her funds. Bob cannot scam her. After the request is made and Bob agrees, he returns the two invoices. Alice's browser verifies the amounts and she is displayed the deposit invoice. Alice now needs to pay the deposit invoice. We'll do so with a desktop client, but it would work the same way from a smartphone browser, or a separate device could be used to scan the QR code displayed. Alice pays the amount requested from her Lightning Network wallet. Immediately, Bob's server detects this payment and triggers the publication of an EVM transaction. This transaction updates the contract to create Alice's requested swap instance. Once mined, it will also give Alice the supercavitation Wei she requires to claim the funds herself, in the case that she didn't already have enough gas. Alice waits for the transaction to be mined, and her browser confirms the details of the newly created on-chain swap instance before presenting her with the settlement invoice. At this point, Alice knows that if she pays the settlement invoice, she'll have everything she needs to claim the funds, so she can safely make the payment. After Alice pays the settlement invoice, Bob knows that she can claim the reward at any time, so he is incentivized to claim the closed reward for himself. Bob publishes a transaction that settles the swap on Alice's behalf, giving Bob a small reward and Alice a better user experience. Once this transaction is mined, the swap is settled. Bob has received Lightning Network Bitcoin and Alice has received RSK. To demonstrate the trustless nature of the system, let's perform another swap, but this time we'll have Bob disappear after Alice pays the settlement, forcing Alice to publish the settlement transaction herself. Here's another swap offering from Charlie, who has different swap configuration options. We'll create another request, pay the deposit, and fast forward to when the swap creation transaction has been mined. At this point, Alice's browser has verified that the swap has been created on-chain to her specifications. This time, we'll intentionally turn off Charlie's web service, so he'll receive the Lightning payment but won't publish the settlement on-chain. We close Charlie's server via SSH, and Alice makes the payment. We can see that the UI is not updated with a settlement transaction as before, because Charlie's not online anymore. Let's copy the pre-image hash. This is the hash of the settlement invoice secret, and is used as a reference to identify the swap. We re-enter it into Charlie's now offline swap offering interface. Even though Charlie's offline, Alice can verify that the swap is still there on-chain and ready to be claimed, so she simply needs to paste the pre-image, the secret she got from paying the invoice, into the UI and publish the settlement transaction herself. She signs the transaction in browser and publishes the signed transaction to the public RSK node. Her private key never leaves her client. Just as before, we see the settlement transaction has been published, but this time from Alice's address. After it is mined, the swap is settled. That concludes the demo. Thanks for watching.